I want to deal now with topic 7 in your textbook, which has to do with electricity in the home. And so first let's look at how electricity actually gets to our houses. Step 1 usually involves, in most cases in the United States, they still use a lot of coal. And so what they do is they burn coal in a furnace which generates steam. Steam will turn a turbine which helps spin a generator. Remember, that's a coiled wire with permanent magnets. And this generator then creates electricity, which goes to a transformer, which we're going to find out is like a solenoid in a way, and it can step up electricity. And then that's sent to either underground or telephone lines above, and then it's sent to another transformer which steps the electricity down into our houses. So two kinds of transformers. Now what can vary is instead of coal, we might use natural gas, which is a lot cleaner. And the natural gas is burnt, which makes steam, which spins a turbine. The turbine acts to spin the generator really fast, which is coiled wire inside a magnetic field and then sent to a transformer. Here's another look at it. So electricity is generated at some sort of power plant. Like I said, that could be coal power, which isn't as clean. It could be natural gas. It could be hydro, so the falling water, which is a lot more renewable and environmentally friendly. We could, at the power plant, we could have geothermal energy, which is renewable, comes from below the earth, geothermal. It could be instead solar cells. So solar cells could create electricity, which is then sent to a transformer which increases the voltage. Then it's sent to power lines, and then it's sent to another transformer that decreases the voltage before it goes into our houses. Remember, in North America, our houses have about 110 volts. So one more look at it. So here's what happens. Power generating station, then a step-up transformer, which goes underground or above, a substation, then another distribution station, and then a step-down transformer, depending, could be which steps it down to 240 to 120 volts. So we've been talking about step-up and step-down transformers. Let's see what they look like. So we have a soft iron core, and what happens is electricity can come through this wire around the loops and then be transmitted through magnetism back here, and then that can move the electricity through the wires here to the output. And here's what a step-up transformer looks like. This is a step-up transformer because when the electrons come this way and then they exit this way, if we have more coils of wire on this side, which is the output, than we do the input, we can step electricity up, which means we ramp up the voltage. Now in this case, let's say electricity is stepped down. Electron flow goes this way through these coils, and then it comes out this way, or sorry, no, it comes in this way, and this is the input, and there are lots of coils. But if you notice, the output has less coils, so the electricity steps down like this. So it comes in maybe at could be many kilovolts, and then depending on the number of coils of wire coming out, we could step it down. Next, I want to talk about how they calculate power. So by definition, power is the rate at which energy is used per unit of time, in our case energy in the form of electricity. And so one formula that we can use to calculate power is the amount of energy in joules divided by the time. Or when we're dealing with electricity, we can find power from a device by knowing its current in amps times by the voltage. So two possible formulas here. So let's try it. Let's say we have a microwave oven. Its power rating is 800 watts. So if you cook a roast in 30 minutes at high setting, how many joules of electricity are converted in the process of this? So let's put in what we know. So power equals energy in the form of joules divided by time, which should be in seconds. Let's plug in our numbers. We know power, the power rating, that's 800 watts for the microwave, which is equal to the energy, which we don't know, in J for joules. We're trying to find that out. And we know the time in minutes, but we have to convert that to seconds. So 30 minutes times 60 seconds in a minute over 1 minute. And so these we can get rid of. So let's multiply both sides of this by 60, and we'll times this side by 60 to get rid of that. And all we have left is so many joules is equal to 800 watts times 60. So that's 48 with 3 zeros. And our units are joules. So 48,000 joules, or if we convert it to kilojoules, 1, 2, 3, 48 kilojoules. Let's try another one. A hairdryer has a 1,000 watt rating. It's 120 volts. So how much current is flowing through there? Well, let's write down what we know. So we know another formula for power equals voltage times current. So what do we know now? We know the power, which is 1,000 watts. We know the voltage, which is 120 volts. And so we just need to times that by so many amps of current. So let's divide both sides by 1,200. So this side divide by 1,200 and divide this side by 1,200. Sorry, 120, and that will give us our answer. And so let's reveal what we should find here. So 1,000 divided by 120 will be 8.3 amps. Let's try one more. So the current is 1.36 and it's passing through a 110 volt outlet. So step one, what's our formula? Power is current times voltage. So if we put our current in, that's from the problem, 1.36, and our voltage is 120. We multiply those two together and we get 1,496 watts, or divide by 1,000, that's 1.946 kilowatts. One more problem. The last one we're going to do is a family uses 3,000 kilowatt hours of electricity in a 2-month period. If the energy costs 11 cents per hour, what would the electricity bill be in dollars? Well, we know what the rate is. It's 3,000 kilowatts per hour. And we know how much in cents. We convert that to dollars. And then we times the two, and that would be $330 for the phone bill. So this is a quick overview of how we work topic 7.